Okay, great. Thank you very much, Vijay. And Vijay will be sending you some further instructional materials by email. And I'll just leave it at that. But you will have a complete resource to learn statistics when you get these this additional resource. Okay, so look, there's three things that I want to tell you about today. Okay, last time I talked about Bayesian inference, where essentially we were starting out with some prior distribution before, and we did an experiment, and we got a much narrower distribution after the experiment. Okay, now the three things I'm going to tell you today are, first of all, that you can actually do much better if instead of estimating the distribution, you actually estimate a point, and it's going to turn out to be the mode or the maximum of a distribution. And it also will turn out that by giving up something, you get much more back, okay? Because it will turn out we haven't given up the distribution completely, but we can approximate it very well by a normal. By the way, Vijay, did you cover the central limit theorem? Oh, good. That we will still be able to have a good approximation of the distribution. And then the third thing that I want to explain to you today, which is the best part of all, is it turns out that in a certain sense, this is the best we can do. Okay? So, I forget where the, oh, there's not too many people sitting on the left. We're interested in the state of nature, theta, okay? State of nature. Okay, and it's a parameter. And I don't think I'll get to the multidimensional case, but that's all in the notes, okay? And by the way, the stuff I'm going to talk about today is in lectures 9 to 11 in the notes, okay? And there's a lot more there, including examples. So we're interested in the state of nature, and we're estimating it from X, the data. Okay? Now, we need a model to describe the relationship between theta and x, okay? And specifically, x given theta is a random variable with a distribution, if it's discrete, the probability function of x given theta, or f of x given theta. So for example, if you're doing some electoral poll, then theta would be the fraction of votes, and x would be the number of 100 people sampled who are voting for your favorite candidate. And so in that particular case, P of x given theta is given by the binomial distribution. Okay, this will fit in very closely with stuff that Kavita talked about yesterday. And so that will be 100 choose x, theta to the x, 1 minus theta to the 100 minus x, etc. Okay? If you were doing it in other contexts, this would be normal. Okay? In fact, most frequently this distribution is normal because of the central limit theorem. You have good arguments often that the data is normal. So look, the ideal thing that we would want to do is we would like to find what we have is x. Okay, we have, and we know something about x given theta. Okay, but what we want is f of x given theta. Okay. Oh, sorry. I mean, we want f of theta given x. Excuse me. Okay, now, what we were doing yesterday, we used Bayes' theorem. Okay, so what Bayes gave us was that f of x given theta was proportional to two terms, f of theta, okay, the density of theta times, this is really embarrassing. I keep writing the theta and the x backwards. That's f of theta given x is f of theta times f of x given theta. Okay, this was the prior. This is the likelihood. Okay, now this gives us what we want, but we need f of theta. Okay, and I touched on the issue that f of theta is rather controversial. You know, how do we get it? What does it mean? It's all a little fuzzy. Okay, so we're going to make a much more limited goal. Okay, we're not going to use the prior. We're going to work with the likelihood directly. And then we are going to estimate a point, not a distribution. Okay? We treat theta as fixed and x as random. Okay? What we want is we want an estimate of theta hat, which is some function of the data, and we want it to be close. We want theta hat to be close to theta. And essentially, what that means is that we have a situation where, okay, theta hat depends on x, and theta hat essentially is a function of the data. Okay, so theta hat is a function of x1, x2, xn. Okay, now, this ties back to stuff that Vijay said. Okay, these x's, data, are random variables. So theta hat is also a random variable. Okay, so I know that in lecture 1, Vijay talked about functions of random variables. Okay, so this is a situation with a function of a random variable. Okay, now in general, this can be very complicated, although there's cases where you can work it out exactly and check the quality of your approximation. Okay, but the point is that we haven't given up the idea of having a distribution in the answer because theta hat is random. It is a random variable, and consequently, it has a density. Okay, so we can write the density as f sub theta hat of x, or more carefully, we could write it as f sub theta hat of x given theta. In other words, this is the state of nature, and then we observe these x's given the state of nature. Okay, since it is a random variable, it will have a distribution. Here is theta. Okay, and what we would like is What we would like is we would like this distribution to be as concentrated, as tight around the true state of nature theta as possible. We would like it to be as close as possible. Okay, so the first thing I want to tell you is, how do you measure that? Okay, so there's quality measurements, and it turns out that these quality measurements have the quality measurement has two components. Okay, so let me give you some definitions. Okay, so there's a term here called bias. Okay, so we say that theta hat is unbiased if the expectation of theta hat equals theta, whatever theta may be. Okay, so essentially we're saying, in terms of the formal definition of expectations, that the integral from minus infinity to infinity of f sub theta hat x f sub theta hat sorry. X f sub theta hat x given theta dx equals theta. Okay, now we can define, that's the definition of unbiased. Okay, the definition of bias is then the difference between the expectation of theta hat and the true state of nature theta. Okay, we can also define something that is actually useful in all sorts of statistical applications that I won't discuss. For example, the lasso. You could look at the error in terms of absolute value. That would be the expectation of the absolute value of theta hat minus theta. Okay, but what turns out to be much more useful is the mean squared error. Okay, and henceforward I will always write this as the MSE. MSE meaning mean squared error. Okay, and that is the expectation of theta hat minus theta quantity squared. Now, it turns out that the MSE has an extremely clear interpretation. It's extremely straightforward to work it out. It's worked out in the notes. This is an easy exercise for the student, okay, which is that the MSE of theta hat is equal to the variance of theta hat plus the bias squared. Okay, this is the error from the spread of data points. If they're more spread out, you'll have a more spread out estimate, because you never get something from nothing. There is no free lunch. And this is the error from bias. Okay, and this is essentially the expected error. Okay, and so, you know, in fact, in general situations, you would think, well, of course, I don't want I certainly would never want to use an estimator that was biased. That would be bad. Well, often it is bad, but it really depends on the circumstances. Okay, so for example, you could have a situation where your estimator isn't biased, but the variance is big, and you could have another situation where the variance is small, but the estimator is biased. Okay, and actually this would give you a better answer. Okay, so, you know, I was talking to one student here last night at dinner, and he was saying, well, you know, there's a lot of stuff happening here, and it's hard to follow all of it. So the point is, what you should be getting out of these lectures is where you should go look up something if you have a serious problem that, you know, you have to use these techniques for. And I'm putting in this plug now, especially for likelihood. So if you look at the notes, there's some very simple cases where there's comparisons of different estimators. And if you have special situations with small numbers of data points, you will not want to use the estimators that I'm going to talk about in this lecture. There's all sorts of special estimators out there. Okay, furthermore, a lot of what I am going to tell you in this lecture is based on the so-called asymptotic theory of estimators. Okay, which is as you keep adding more and more points, you look for limits. And you can prove beautiful theorems about these limits. However, those results are not useful if you happen to have a small number of points. And in such a case, you may want to go look for a special method that is suitable for your problem. So this is how we're going to measure how well we're doing. And then the question is, where are we going to get these estimators? Okay, there's lots of places we can get them, but one source is maximum likelihood. And that's what I'm going to talk about today. Okay, so recall what we did for Bayes. We had a prior and a likelihood. Okay? And so, in some sense, it's perfectly reasonable to look for maximum likelihood. We're essentially looking for the mode of this distribution. Now, we have this problem that f of theta is not available. In fact, suppose f of theta is flat. It's uniform. Okay, that's not much prior information, and actually people who do Bayesian stuff in practice, that is the most common prior used. If the prior was flat, okay, maximizing the likelihood would be a really good estimate to find theta, okay, if we just made it as large as possible. Okay, and we're going to call that theta hat. Okay, so for max likelihood, okay, and sometimes called MLE, we're going to define L of theta, which is f of x1, xn, okay, given theta, okay, these are lowercase x's. They are the realization of the n random variables of the data. Okay, so this is our f of x given theta. This is the likelihood function. Okay. Now, the value of theta hat for which I don't need to write that down, for which, well, okay, this is the maximum likelihood estimator. Now, what does this mean? Okay, if you are a Bayesian, okay, and there's this, if you were a Bayesian, then essentially what you would say is this is going to be the maximization of theta given x if the prior is uniform, okay? And if you're not a Bayesian, then you would say that L of theta is the probability density that we observe the data that we actually observe, given that the true state of nature is theta, okay? And so the idea then is the maximum likely estimator theta hat is the state of nature that best explains the data and for which it is the most likely. Okay, now I had problems yesterday essentially giving too many examples, but I want to give one example today that actually fits right in with what Kavita was talking about yesterday, and indeed into a specific question that was asked about estimating diversity of populations. Okay, so suppose Kavita was talking about a situation where the data, which in this case was sequences of genes, came from a binomial distribution. Okay, so in that particular case, L of theta was given by n, choose x, times theta to the x times 1 minus theta to the n minus x. And note that I mentioned logs here, okay? So if you maximize L of theta, or you maximize the logarithm of L of theta, that's the same as maximizing theta. And the reason that we're going to be doing this a lot, okay, is that it is frequently the case that these random variables that compose the experimental data are independently and identically distributed, okay? And as you know from Vijay's lecture, okay, if you have random variables that are independent, then the probability of the whole set is going to be the product of each one separately. Okay, so if you have IID random variables, this function is going to break up into a big product, and when you take the logarithm, it's going to end up being a sum, and everything will be nice and computable. Okay, now this likelihood function, okay, so in this case, if we maximize the log, that's the same as maximizing log of n choose x plus x log theta plus n minus x log 1 minus theta. Okay? And, you know, we have a situation for a binomial distribution. The likelihood is going to look something like this. Okay, maybe if the data was good, I could have drawn that a little tighter. And theta hat is going to be here. Okay, so how do we estimate the maximum? Okay, well, this is not an advanced problem. You do it by setting the derivative equal to 0 and checking the second derivative to be sure it has the right sign. Okay, and if you're doing it, I won't talk about multiple dimensions, but the generalization is straightforward. Okay, so what we want to do is we want to set 0 equal to the derivative with respect to theta of the log of L of theta. And so what's that going to be? Okay, well, the derivative of this with respect to theta is 0. There's no theta there. Here the derivative is going to be x over theta and minus n minus x over 1 minus theta. Okay, and if you solve this, okay, you can see that you want theta hat equals x over n, okay, a quantity that came up in Kavita's lecture for estimating diversity of alleles. Okay, now you want to be extremely careful. Okay, what the second derivative with respect to theta in this case is going to be minus x over theta squared minus n minus x over 1 minus theta squared and both of these terms have theta squareds and they have negative signs in front of them, so it's not a difficult computation to see that this is less than 0. Okay, so there's lots of further examples in the notes. Depending on how time goes, I'll pose them as exercises. A lot of the, fortunately or unfortunately, you will not have to do homework problems, but you can. Okay, and some of the material that the material that VJ will distribute to you includes exercises with answers. Now, I think I've touched on the fact that the maximum likelihood estimator is not always the thing that you want. Okay, it has good sampling properties as the asymptotic limit of large data is approached, and but it doesn't always have the smallest MSE. Okay, but there's a lot of theory connected to this that I won't get into. Essentially, if you have large enough samples, it turns out that in a lot of useful senses, the MLE is frequently the best estimator, and that's why it's the one that gets taught. Okay, now there's some stuff that I'm not going to cover today, and you might want to have a look at Lecture 10. Because it has a lot of interesting infrastructure that I'm not going to have time to get into. In particular, it derives the chi-squared distribution. And I'm going to be talking about the chi-squared distribution in the next lecture about hypothesis testing. Okay, the chi-squared distribution is the sum of squared normal random variables, and it will come up a lot. And the other interesting example that's in Lecture 10, and you know, maybe I'm doing well enough for time, so I'll sort of describe it to you verbally, okay, is I just gave you an example where you're finding the maximum likelihood estimator by taking the zero of a derivative. Okay, well, that doesn't always work. Now, when might it not work? Okay, well, it won't work if the maximum is actually at the edge of the domain. Okay, so there's a beautiful and famous problem that's treated both in the discrete and the continuous case. Okay, so in the discrete case, this is a famous problem from World War II for spies. Okay, and the problem was to estimate the size of German tank production from captured tank engines. And in order to estimate production, you needed to know the serial number of the tank engines. And so the question was, if you observe serial numbers from captured tanks, okay, what is your estimate of the maximum serial number? Okay, so it actually turns out in that particular case that maximum likelihood estimator will basically turn out to be the largest serial number that you've observed. Okay, so if you find this at all interesting, okay, it's worthwhile to check that, to read about that in lecture 6. Okay, oh, and there's another example you can work out as an exercise. Okay, so suppose you have, this was a binomial example. Okay, suppose you're interested in estimating the mean failure rate of some component. Okay, so if you have a constant unknown failure rate, then what happens is that you have
John?
Yeah.
Before you go, I mean, just a question to
yes.
everybody. So, I mean, so if I have data from an experiment,
right,
and I don't know the model likelihood or something like that, then how do I estimate the maximum likelihood of the parameters, or do I really need to write down some?
You absolutely need to have a model to use maximum likelihood. Okay, so there is always a model whenever you do statistical inference. Okay, and to compare the sort of thing in statistical inference with what I'm going to be talking about later, okay, this issue has come up about various kinds of prior knowledge. So it usually turns out in purely statistical inferences, and all the classic stuff, the models are really simple. Okay, you're asking really simple questions like, is the mean of two samples, is the mean really different? Okay, so in all this classical stuff, the models are very simple. Now, what happens in real life is you sometimes work with much more complicated models. So I'm not even going to talk about linear regression in these lectures. Okay, I can tell you that one of the things I will talk about next week is a differential equation model that is essentially fit from data by what we hope is maximum likelihood. Okay, but the model is extremely complicated, and there is no clear statistical method. Okay, I will even go a step or two further. Okay, and I'm looking at my watch because I'm very conscious of running out of time yesterday. Okay, a lot of the stuff that's happening on the frontiers of statistics, okay, and things that you are actually likely to run into in specific applications that you use. For example, there's this word data science, okay? I think the word is kind of flaky because, look, if you don't have data, you're not doing science. So, but a lot of what data science turns out to be in practice is you have huge data sets, okay? Who's friends with who on Facebook? Okay, if you're a spy, you know, who's plotting with who, okay? And you have statistical problem, and there's all data mining, okay? There's all sorts of interesting algorithms, okay, that are used on these problems, okay? So I'll say a word, the lasso method, okay? I won't tell you what it is, but you'll run into it, okay? And there's many other examples. It generally is the case that there are people are developing, it is a current frontier area in statistics, to develop good probabilistic models for these methods. They are frequently absent. Okay, now what happens? What happens if you face such a problem yourself? Okay, what are you going to do? Okay, you can't throw up your hands and say, oh no, I can't do this because I don't know all this stuff that Reinitz was writing on the board for this problem. Okay, you basically have to do the best you can. Okay, why should you know this stuff? Okay, well, because you should be thinking about it this way. Even if you can't get the clean answer in terms of these beautiful distributions and these simple problems that you can solve analytically. Okay, so you don't have to do homework from these lectures. Okay, but you should take away the big concepts so that when you have some problem of your own, you can apply it effectively. Okay? Now, are there any more questions before I go on? No? Okay. Okay, so a problem that I'm not going to solve, but I'll give as an exercise is the mean failure rate. Okay, suppose that a component has a constant probability of failure, okay? So that it lasts for some time x, okay, with the distribution f of x given theta, which is 1 over theta e to the minus x over theta for theta greater than 0, x greater than 0, 0 otherwise. And you can show that the expectation of x, in fact, is theta. Okay, now, suppose your problem is that the mean failure time theta is unknown. Have f of x given theta, and you want to estimate theta. Okay, so it will turn out, since you can write, and these x's that you're measuring, which is the failure of each individual component, okay, n components were tested independently, okay, to observe x1 to xn, okay, then your problem is to estimate theta, okay, and this is one of the cases where independence will help you, okay, these variables are independent and identically distributed. This IID is something you'll see all over the place in statistics books, and so the joint density of x sub 1 to x sub n given theta is just a big product f of x1 theta f of x sub n given theta. Okay, this writing it as a product is the absolute key point. Okay, now I'm not going to go through the details of how you do this because I'm leaving this as an exercise for you. Okay, but basically you should show that theta hat is simply the sample mean, x bar. Probably Vijay told you what the sample mean is. That's simply 1 over n times the summation of the x sub I. Okay, and furthermore, that you can then easily get the MSE, and you can show that the MSE of theta hat is equal to theta squared over n. Okay, and you can also check that, in fact, in this case, it's unbiased. The expectation of theta hat equals theta. Okay, this is a very straightforward calculation. Okay, now if you were actually taking a class in this from me, okay, and people come to my office to ask for help, okay, the thing that people have the hardest thing to understand is this key step of breaking things into this big product. Okay, and once you understand this, you can understand how to derive maximum likelihood estimators in lots of contexts. Yeah.
The first, when we were doing, and we know the f of theta, the distribution of theta, and then we went in maximizing the likelihood. You said either we do not know theta or we do not know the distribution of theta.
Well, at the beginning of the problem, we don't know the distribution of theta, and furthermore, we don't know theta, and we don't know the distribution of theta.
Yeah, the question that I want to ask, the way you maximize the likelihood and then predicted theta cap, the possible state of nature. So it is becoming totally model dependent now.
Yes.
So suppose I work on model 2 and you work on model 1 on the same problem. So in that case, we are going to get different theta cap or
Yes.
different state of nature. So how can we be sure that our model are right? So we are going to get different answers for different models.
That's a real problem. Okay, there are ways to compare models. Okay, and sometimes I'm not going to be able to cover them. Okay, this is something that you have to look into in connection with your problem. But there's no sort of simple answer to that question, and it's a really, really, really good question. Although one part of the question naturally feeds into the next thing that I want to talk about, which is the issue of the distribution of theta hat. Okay, because I told you how to work out maximum likelihood, and if you're not worrying too much, you think, oh great, well that makes perfect sense. I can just do a whole bunch of problems now, and I understand things. Okay, but theta hat is a random variable. It has a distribution. Okay, what can you say? You want the distribution to be tight. Okay, what can you say about that? Okay, now I'm going to take a small risk here and move back to the left. Okay, but I want to tell you about my favorite part of maximum likelihood theory. Okay, this is a really, really nice piece of work. And actually, you know, I haven't posted it, but, you know, one thing I tell my class is that you can tell how advanced mathematics is by when it was invented. Okay, and this can be very depressing if you're a student, because calculus is 400 years old. And in general, things from the 20th century are, you know, often kind of incomprehensible to a fruit fly biologist like me. But the result I'm going to give you is from 1923. It's from a very long paper by Fisher about maximum likelihood. And the proof, while not completely rigorous by modern standards, is really quite elementary. Okay, so let me not run out of time. Okay, so having given you this big buildup, I'm now going to tell you about Fisher's, and I have to write slow so you can read my handwriting, about Fisher's approximation theorem. Okay, so what it says is, if the MLE can be found from solving the derivative of the likelihood equal to 0, or in practice, of course, what you're really likely to do is solve the derivative with respect to theta of the log likelihood. Okay, then theta hat has an approximately normal distribution. When the number of points is large. Okay, I've already mentioned the cases where this might not necessarily apply, which is if the estimator is at the edge of the domain. So this theorem applies to maximum likelihood estimators that are in the interior of the domain. Okay, and it means that theta hat is approximately unbiased, okay? Okay, that's because of the shape of the normal distribution, okay? And it also means that the MSE, because of this, that the MSE of theta hat is going to be the variance of the normal distribution, okay, which is going to be 1 over tau sub n. Okay, now I'm going to tell you how we get tau sub n in a moment. Okay, so this is sort of like the resurrection of what we gave up by going from Bayesian to point estimation. Okay, it looked like we were giving up a lot, no more distributions about the answer, but it's not really true. It turns out that as many things work out in statistics, if we have enough points, things are going to work really smoothly. Okay, now how do we find tau sub n? Okay, so I'm going to give you the IID case only. Okay, because it's simple to figure out. Okay, the non-IID case is dealt with in the notes. Okay, the full general non-IID case is kind of a mess. But let me not distract you. Okay, in the IID case, the likelihood so I want to write the answer down here. Okay, so in the IID case, the likelihood, as I've been mentioning, is a big product from I equals 1 to n of f of x sub I given theta. Okay? And in that case, tau sub n squared, okay, will be equal to tau squared over n. And this is something that I'm sure Vijay brought up in connection with the central. No. Okay. Yes. Okay. So the point. This is also Kavita mentioned this. This is something you should have ingrained in your mental DNA. Okay. That if you're looking at a random situation, the variance goes as 1 over n, which means the variance is essentially the square of the uncertainty. Okay, so your error tends to have this square root of n crops up. Okay, this is a really fundamental thing. And after carefully looking at my watch, I'll just add that historically, in the history of developing these statistical ideas, it was actually very difficult to find this. Okay, this was quite a non-trivial result, and it wasn't figured out until early in the 19th century. Okay, so this is another example. This shows you why you want to have a lot of points. Okay, because you can make tau sub n smaller by increasing n. Okay, now what I will not prove. Okay, yes, a question. I'm sorry. Excuse me? Oh, Vijay, thank you. Occasionally I'm horrified by something that I forgot to do, and I don't like to call attention to my own mistakes, but in this case it's pedagogically advantageous because this is so important. With a theta hat has an approximately normal distribution with variance um, 1 over tau sub n squared. Thank you so much for asking me that, okay? Because this is the whole key to the point, okay? See, I'm building up the suspense. Yes, what is tau, you might well ask. Okay, and so I'm just going to give you the answer. And if you look in the notes, you will see a non-rigorous proof of this. Okay, it's the section, I think in lecture 11, that's labeled Ideas for Proof of Fisher's Theorem. Okay? So I'm not going to give you tau sub n in full generality. I'm going to give you tau, okay, for IID, and you can construct tau sub n by dividing by n. Okay, so 1 over tau squared is equal to the expectation of the partial derivative with respect to theta of the log of f of, okay, I'm writing x1 given theta, okay, because without loss of generality, if the data is independently and identically distributed, if you work this out for 1 point, you can work it out for n points just by dividing tau squared by n. It's this expectation squared, okay, and that turns out to be the same, okay. The derivation is given in the notes. I'm not going to try to do it in class. If you don't like squaring things, it turns out to be exactly the same as the expectation of the second derivative with respect to theta of the log of f of x given theta. Okay? Don't be confused because I left out the n. Okay? I could have put the n in and written a more general formula. There's some examples in the notes. Okay? Students who do homework problems about this, okay, the thing they have a lot of trouble getting is that if you have independently and identically distributed data and you have to actually work this out for some specific case, okay, you can take a really big shortcut and work it out for 1 point, okay, and then when you find the variance, you divide by n, okay, and you can check oh, of course it depends on x. X is the data. Yes, as is completely natural. Okay, everything about the estimator should depend on the data. Okay, so let me sort of restate, okay, at the risk of being boring, but they say the soul of pedagogy is at least a little repetition. Okay, we gave up these Bayesian posterior. Okay, we went to what seemed to be a much cruder situation where we were just estimating the mode of the likelihood. But it turned out we were looking at functions of a random variable. The data is a random variable. The estimator of the state of nature is therefore a random variable that is a function of the data. Think functions of random variables. And then, just as it turns out that so many things in statistics can be approximated by normal distributions, it turned out we got our distribution back when we do the maximum likelihood. Okay, not only did we get our distribution back, it's normal. It's normal. It has a variance that is given by this formula. The variance has all the properties that you would expect, okay? Just I'll write it again, okay? That 1 over tau sub n in the IID case is, or that tau sub n is simply tau over n. Okay, so we have a distribution here, and it's normal. All the things we care about, both its mean and its variance, depend on the data. They depend on the distributions of the data. Okay, usually normal, but not always. Okay, this is exactly what we want. This is one of the things you should take away from the lecture, okay? For various reasons, I've had it. For example, there's certain areas where people learn statistics like some kind of set of magic tricks, okay? And I mean no insult if any of you are physicians, but the clinical literature is particularly prone to this. And I think that everyone who actually does statistics on an actual problem, you should really have to know Fisher's approximation theorem, because you'll read some newspaper article somewhere, okay, that says if such and such were done, 15 lives a year would be saved. Okay? But of course, if you worked it out with Fisher's theorem, your answer would actually be that if such and such were done, 15 lives plus or minus 75 would be saved. Okay? And that gives you a very different picture. Okay? So this is very important. Yes.
Are there any conditions on f(x) theta for this formula to be valid, or?
The only condition is that the maximum likelihood must be in the interior of the domain. Okay? In other words, it's a differentiability condition. It's a differentiability condition. And this is, I point this out because this is just something that you should be conscious of. Okay? These are a set of ideas. They work out the formulas in the simple case, okay, but you guys are here to train to do research, okay, so you won't be doing actual problems in the simple case. You'll be doing it in a complicated case. But these ideas, okay, will form the basis of what you do nevertheless. Yes?
And the generalization to non-IIDs will be something similar or some really different?
Well, okay. If it's non-IID, it's essentially the same idea. Okay, so the notes have some slightly grisly examples that if I went through them on the chalkboard with my slow writing of equations would be just suicidal to the organization of this lecture. But there's some specifically non-IID examples there. Okay, look, in reality, the worst sort of limit on all of this is that this essentially presupposes that you have an analytic picture of the distributions beforehand and afterwards. Okay, so in real life, you are really dealing with nature, which is nature. It can get messy. Okay, that's the way things are. Yes? Yeah?
It's turning out to be proportional to n. Am I missing something here? So variance is 1 over tau n square.
Yes.
And here tau n is.
What did I do here?
My guess would be that tau n square is the variance.
Excuse me?
I mean.
Yeah, it's. I'm sorry. I'm a moron. One over tau n will come up later. Thank you so much for asking that question. Yes. Okay. This is my secret reason for not using the board, because I get excited. I love Fisher's theorem. Yes?
That expression, the xi's, are these the data points, x1, x2?
Yes.
So they are like realizations of the random variable, right?
Yes.
So you're saying that the data points are IID,
yes, in this particular case, the data points are IID.
What does that mean, like data point? They are realizations of the random variable are independent,
What does IID mean?
Yeah, IID.
Oh, okay, that's worth repeating, okay? IID, you get it a lot, okay? Independently and identically distributed. Got it?
Usually IID with respect to random variables, right? But here you are saying that the realizations are independent of each other, or what?
Well, you see, the data is a random variable, but when you do the experiment, the measurements that you're taking, that you actually have, are realizations of that random variable. So when you're working out the estimator, okay, you want to think of the x's as random variables. However, when you're actually looking at the results of some experiment, okay, of course, you don't have random variables. You always have realizations when you do the measurement, okay? And this is, you know, when I give the probability lectures and I have, you know, full time to expound, okay, I give a big speech about random variables because I personally had a really hard time understanding random variables. You know, the tricky thing about them is they're sort of like blurs, and every time you look at them, a little point comes out, okay, but not quite the same one. And then things get even trickier when you have functions of random variables, okay? And there's essentially no loss of generality at the conceptual level from just considering the IID case. There can be really ugly things that happen if you have a non-IID case and you actually want to work it out carefully. Okay, but there's a lot of things that, you know, people talk about the IID case a lot because it has such beautiful properties. And it doesn't mean you're cheating because you have the beautiful properties. A lot of times in practical situations, you know, you use that and then you say, okay, and what are the possible sources of error, you know, to the whole procedure that I used? Okay, now, do we have any more questions? And particularly possible mistakes I made on the board, okay? You know, I stand before you as someone who doesn't always quite write the right variable sometimes. So it's helpful to me and everyone if you find mistakes. Yes?
Just, as that 1 by tau n was changed to tau, and I'm just asking that equation 1 by tau, should that be 1 by tau or tau? Just asking that thing.
Where do I have
that equation, IID, 1 by tau equal to expectation of del del theta, that equation?
Thank you. Yeah, you'll see in a minute why I was writing 1 over tau sub n. I was actually thinking ahead too much to the third part of the lecture, which now I think I really should get to, because I see from my watch I have 22 minutes, and that includes the time that's supposed to be for questions. Okay, but I think I have just enough time. I think I have just enough time to tell you about the last major result, which to me is the sweetest of all, because it's saying that there is a certain sense in which the situation I've described is really the best you can do given the data. Okay? So, in order to talk about what's the best you can do, okay, suppose that you're comparing two different, so the question is, you could use all sorts of different estimators, okay, and if you look at the notes, you'll see a plethora of examples, some of which do better than the MLE on cases with a small number of data points. Okay, suppose that you're comparing two estimators, we'll call them theta hat and theta tilde. Okay, and suppose they're unbiased. Okay, so that means that the MSE of theta hat is going to be the variance of theta hat, okay, plus, well, there's plus the bias, okay, I just erased the definition, but it's 0. Okay, similarly, the MSE of theta tilde is simply going to be the variance of theta tilde, okay, because the bias, again, goes to 0. Okay, and both estimators are conditioned against the same data. Okay, and so essentially, we're going to prefer theta hat if it has a smaller variance than theta tilde. Okay, so we could define something we could call the effectiveness of the estimator or the efficacy ratio, okay, between them, between theta hat and theta tilde, to be the ratio of their variances, okay, the variance variance of theta tilde over the variance of theta hat. And if this is greater than 1, we're going to prefer theta hat because it has the smaller variance. Okay, and of course it's going to be like that because if the data is IID, then if the variance of theta tilde is C1 over n, and the variance of theta hat is C2 over n, okay? You might be designing an experiment, and then you want to ask yourself, how many points do I need to measure so that my estimator has such and such an accuracy? Okay, well, of course you want to use the best estimator possible, because if you use the best estimator, you can use the smallest number of data points in your experiment. Okay, so this needs a whole board of itself. Okay, so I want to tell you without proof another beautiful result, and I'm sure that I'll break it, but it's such a beautiful result that I'm going to use a fresh piece of chalk. Oh, yes, question.
Just clarifying, are you defining the numerator larger than the denominator in this effective?
Yeah, this is just an example, okay? Yes, I am, okay? I'm saying, yes, you would prefer theta hat, okay? And I'm actually, I may have made it almost less clear by writing the equation, okay? I'm basically stating essentially a fairly obvious point, okay? Which is...
Like, you don't know the variance with...
Oh, just wait. I'm going to give a result, okay? All I'm really saying here is, suppose you have to choose between two estimators that are both unbiased. Obviously, you want to pick the one with the smaller variance, right? Okay, okay, well, I haven't told you how to pick or anything else. Okay, now, as I said, I'm still not dead as regards to time. Okay, so there is a measurement of efficiency of these estimators, okay, and it's called the Cramer-Rao inequality. Okay, so let x1 to xn, okay, be IID, okay, Remember, IID, independently, identically distributed with density f of x given theta. Okay. Let t equals t of x1, xn, be an unbiased estimate of theta. Okay, then okay, I've just introduced a new piece of notation. Okay, but just to make it completely clear, okay, this is a really beautiful result. Okay, any unbiased estimator you have has the property that the variance is greater than or equal to 1 over n times n times I of theta. Oh, actually, this is 1 over tau squared. Where I of theta is actually 1 over tau squared. Okay, this is the same tau squared as in Fisher's theorem. Okay, and the reason I wrote it as I is this is sometimes called the Fisher information. Okay, so remember I said at the beginning of the lecture that I essentially wanted to make 3 points. Okay, I wanted to tell you how you could compare estimators. Okay, and so that led us to talk about the MSE and the bias. Those are quality measures of estimators. Okay, then I developed the idea of maximum likelihood, and that got us to Fisher's approximation theorem, which said that if we use maximum likelihood, okay, the estimator would be normally distributed, and we got a concrete expression for its variance. Okay, what the Cramer-Rao inequality is telling us is that that's actually the best we can do. Okay, if you had any other estimator that was unbiased, you could not possibly get a tighter variance than you get from the MLE. Okay, and why is this called Fisher information? Okay, well, you can't get blood from a stone, and you can't get information from data that isn't there. Okay, you do your experiment, you get some results, and you'd like them to be as accurate as possible. Okay, but you can't find information that isn't in the data. People may do that, but that's not what we're trying to tell you about here. Okay, so given the assumptions, which are pretty reasonable, okay, IID and N is big, okay, the maximum likelihood estimator by Fisher's theorem and the Cramer-Rao inequality is squeezing the last drop of information out of the data that you can get. Okay, so I'm actually, pleased with myself a little bit because I see that it's now 9 minutes to 11, which means there's time for questions. And I haven't run out of time in the middle. Okay, I sort of had to skip a bunch of stuff, but you can go back and look at that. I apologize to all of you for mistakes I made in writing equations on the blackboard, although this is really good practice for me because actually my students complain that I don't use the board. And I want to thank you in particular, by the way, for pointing out that extremely critical mistake. I just will tell you, we need time for questions, but I really appreciate people correcting my errors. And, the notes you've got, there's 1 or 2 errors still, not in the math, mostly in the examples. Description, okay? But, sometimes the students are shy about emailing me corrections to my posted notes. And there was one young woman in particular, a first-year student from China, and she was so apologetic, She'd send me these emails saying, oh, I'm so sorry to be so picky, but, in lecture 12, in the equation on page 17, is this something right here? And what about over here? So she was always so apologetic. And I have to say, when she came in to take the final exam, I let people have 1 page of notes. So she had a page of critical equations to take into the exam. And I mean, I'm, getting old, so my eyesight isn't what it used to be. I couldn't even read them. I mean, they were so tiny. And then she took the exam and got 100%. And, I spend a lot of time in this class administering psychotherapy because usually the grades are spread between about 95 and 40. So, 70 is a very respectable grade, and people aren't used to that. Anyway, that story's gone on maybe too long because there are probably at least 1 or 2 questions. Thank you very much. Any questions? Yes?
That Cramer-Rao inequality, if I go to the formula, variance should be greater than equal to 1 by ni. Okay? Yeah. So my question is that it means if the I is small, means as I is 1 by tau, so if I go to the formula of 1 by tau written in the left board.
I'm sorry, what's?
Okay. I equal to 1 by tau.
Right.
And 1 by tau is written in the left board, is the expectation value.
Yeah.
So it means that if tau is proportional to tau n, so if my error is large in the data,
if your n is large
means error is small in the data, tau n or tau is small, suppose.
Yes.
It means the variance of t is going to be large.
Is the what going to be large?
Variance in t, that variance of t is going to be large.
The variance.
When my tau n is smaller. It is in intuition how to understand this. Means smaller error in data, but larger variance. How can that be possible?
No, because I is 1 over tau. I is 1 over tau. So as n gets large, this is saying the variance is greater than or equal to, if you forget, it's greater than or equal to tau. And as you add more points, tau, you go from tau squared for 1 point to tau squared over n. So the variance gets smaller. Okay, I had a moment of fear that I had left something up there that had the uncorrected tau, but any further questions? Yes. Daniel.
Estimator as the parameter that you use to fit your data, right? But you said during the class that Bayesian statisticians.
Sorry, say again?
That people who do Bayesian, is that, how do you pronounce it? Statistics, think of it different. Could you repeat that point, please?
Yeah, I will as soon as I didn't quite get what.
Oh, sorry. So there are 2 ways of thinking about the maximum likelihood estimator.
Okay, which 2?
If I understood correctly from your lecture, there is the classical way and there is the Bayesian way. Is that correct?
In a variation way? Oh,
Bayesian.
Bayesian.
Yes.
Oh, there's two ways to do inference.
Right.
So there's Bayesian and there's maximum likelihood.
Right. So you said you would go for an flat prior, a uniform prior.
Yes, I said that maximum likelihood was like doing Bayesian estimation with a uniform prior.
Could you repeat that point for me, please? So what's the intuition of it?
Well, the intuition is if you work out from Bayes' theorem, okay, and from the notes from the previous lecture, okay, and you write the posterior in that proportionality form, that it's the prior times the likelihood. Okay, what you're doing with maximum likelihood, if you maximize the likelihood, is essentially you're not paying attention to the prior. So if you were a Bayesian by deep conviction,
Looking for.
yeah, then you could basically think about this as being the same as Bayesian estimation, in some sense as being the same as taking a Bayesian estimate if you had a uniform prior. If you were a believer in the idea of priors. Okay, what happens in practice is, you do differently on different cases, depending on your situation, okay? So I'll just say sometimes people get a little bit too religious about this stuff, okay? And it's not a religious question, okay? It's a problem-solving question, okay? So I can't go into the details, okay? But essentially, different circumstances, you use different techniques. Okay, and so for a long time, maximum likelihood was widely preferred to Bayesian because if you're basically doing numerical stuff that you worked out analytically in advance, there's a good analytical theory of the maximum likelihood, of which I've sort of given you like the major highlights today. Okay, with computational techniques, Bayesian inference has become popular, okay, often on very large-scale problems, okay? So people in my lab have used it for estimating phylogenetic trees, okay? One of the things is that if people do it right out of the box, okay, and this sort of happened with the person who was doing this, if they don't know the conceptual basis of Bayesian inference, they're not going to know things like, is there some adjustment you could make to the prior because of knowledge? Okay, there's a kind of a. Do we have any other questions? I'm gonna make a philosophical point, but I will make it short so you have time to ask. There's a sense in which every time you infer something from data, okay, in some kind of global sense, you're always doing it in a Bayesian way, because although these cases I worked out as math examples that were sort of pure, okay, really what you're doing comes from the context of everything else you know. And you may know all kinds of things about some system, okay? I work with these complicated situations in fruit fly embryos. But a lot of the stuff that I apply from prior knowledge, there's no way to codify it mathematically. Okay, so the point is, you have to do the best you can with your whole brain. Okay, that's my little sermon. It's not really science. Yes?
Thanks. This Cramer-Rao inequality ties or seems to tie very well with some model testing, like you're contrasting two sort of variances, and you're saying there's one which can give you the best result and over the other. So how does that tie up with model testing? Just curious.
Gee, what a great final question. Okay, so in this sort of limited sense, I talked about it here on the board. Okay, it's just saying that if you obey the conditions of Fisher's theorem, maximum likelihood is the best estimator you can have. Okay, with various math, the usual kind of math technicalities buried somewhere, but they're true in a very wide variety of areas. Okay, you're actually asking me a question of what happens if you actually have to make a decision from your data. Okay, so that's hypothesis testing. Okay, and so that's a great last question, because that's what I'm going to talk about tomorrow. Okay, and it's sort of like more of this throw things away and therefore gain something. Because first we threw away distributions, but we got back Fisher's theorem. Okay, now we're going to throw away these continuous estimators, and we're going to be interested in really a lot of situations that come up to estimating a bit that's 0 or 1. Okay, you work in the beer plant. Okay, maybe the Guinness Brewery in Dublin. Okay, and you want to know if your batch of beer is good enough to put in bottles or it has to be rejected. Okay, your boss, okay, isn't going to want to sit down and hear an hour about prior and posterior distributions about the quality of the beer. He just wants to know, does the beer ship or not? Okay, that will be the next lecture. Okay, so I think if someone has a burning question, I'm happy to answer, but this seems like a good time to end. Right? Okay, great.